Now, in this section of the podcast, we're going to challenge Marianne to explain a mathematical concept to us in 1 minute. So now, Marianne, we're going to time you while you explain the concept of herd immunity to us. Okay, 3, 2, 1, go.
One very important parameter in epidemiology is the effective reproduction number of a disease. So that's the number of people an infectious person goes on to infect on average. Now, obviously, the bigger that number, the faster the epidemic will spread. And as long as that number, which is normally denoted by R, is bigger than 1, the number of new infections will continue to grow. So, for example, if R is equal to 2, then a single person will infect 2 more people, who will go on to infect 4 more people, who will then go on to infect 8 more people, and so on. The aim of any intervention, whether it's the social distancing we're living through now or vaccination, is to bring the effective reproduction number R to less than 1, because that means that the number of new infections becomes smaller and smaller progressively. When this is the case, then we have herd immunity.
That is great. That was just under 1 minute. Right, but I want to know some more. How does this mathematics of herd immunity, how does that lead to the figure we've heard about so much in the news of needing at least 60% of the population immune from the COVID-19 disease to get herd immunity for this particular disease?
Right, well, for COVID-19, the initial value of R, when everybody in the population was susceptible to catching the disease, was estimated to lie somewhere between 2 and 2.5, roughly. Now, that initial value is called R0. It's the basic reproduction number of the disease. Over time, the proportion of people who are susceptible to catching the disease will decrease from 1, which means everybody is susceptible, to some smaller number, say, for example, a half. Now, if that proportion is called P, then the effective reproduction number R is equal to P times the initial reproduction number R0. So, for example, if we take R0 to be 2.5, and we are at the point in the epidemic where only half the population is susceptible, that is P equals 0.5, then the effective reproduction number R is a half of 2.5, which is 1.25. So this is how you work out the effective reproduction number from the proportion P that are susceptible and the initial reproduction number R0. You can use this mathematical relationship the other way around to understand what proportion you need to be immune in order for the effective reproduction number R to be less than 1, which is what we want for herd immunity. And a back-of-the-envelope calculation tells you that you need a proportion of 0.6 of the population to be immune at least, and that translates to 60%. So to get herd immunity for an R0 of 2.5, we need to get at least 60% of the population not susceptible to catching the disease.
You can find out all the details behind that calculation and the rest of the mathematics we've talked about in this podcast on our website plus.maths.org.